it's Jacob from International Precision Engineering, and today we have a little controls experiment set up. So what we have on the breadboard here is a DC motor, toe clamp down, just to kind of hold it. On the back of the motor is it is an A quad B encoder, but we're only using one channel because we're just only driving this like unipolar driver, so it can only really drive in one direction. So there's no positioning capability, so we don't need the second channel, even though it is there. And we're doing all the control on an Arduino with a simple single transistor and RC filter for circuitry, and it's all on this breadboard. We'll look at it closer. We're using a lab power supply so that we can monitor the current and voltage going into the motor. And then on the oscilloscope, we're looking at the encoder ticks and also the drive voltage coming out of the Arduino. On the laptop here, I just wrote a little LabVIEW script. Basically, all it's doing is reading the calculated not RPM, but tick like clocks per second off the encoder, so cycles per second. And then that's what we're servoing to, and then we have just a couple controls where we can change our PID parameters. So let's take a closer look. On the screen here you can see that we have 4 knobs, one for our set point, and this is, it says like 0 to 3.2, but that's 0 to 3,200, and it's not RPMs, it's clicks per second on the encoder. And in this little box we have the calculated RPM coming back from the Arduino, and you can see that, like for example right here, it split the line and it did it again, right? So on this chart what we're plotting here is the white is the measured RPM, and then the red line is our set point, and then every single squiggle here like this where it goes crazy is because it split the line. On the top here we just have basically what we're sending to the Arduino. Right now it's just the set point, we have our gains turned off. And then on the 4 boxes over here it just tells us exactly what the knobs are set to. So you can see the white line, which is our measured RPM on the chart, is following pretty closely to that set point. So if I go and move it, if I turn it up, you can see immediately the red line jumps up, and then soon after the white line follows, right? So right now our motor is following pretty closely to our set point. And then again I could turn it down, we'll say like go to here. Once again our set point falls, and then our servo kind of follows. So right here, this squiggly line, it's the servo's hunting, so it's going too fast, it's going too slow, it's speeding up, and it's just kind of trying to find its place. But then it does settle down and the motor starts running pretty good. On the oscilloscope we're looking at 2 channels. The green is the actual encoder pulses, and the yellow line is our filtered PWM signal that's going into the base of the transistor. So if we turn these up and sort of dilate our time scale here, the only thing that matters here is your period. And then I'm measuring frequency, so right, our set point according to the screen here is 2.8, and we're sort of hunting right around 2.8, 2.7, 2.9. And our supply voltage to the base of the transistor is 4.6, so we're almost at full power here at like 2.8. If I bring it down to 2000, you can see the power will drop off a little bit down to 4 volts, and we're sitting at 2.3, 2.2, 2.3, something like that. So, and this dial's not perfect, but you kind of get the point. So here's the mess of a circuit that we have, or more of really like a rat's nest. But you know, it's actually not too bad, and I'll draw it out on the screen and we can walk through it. But A lot of these are, so like this thing's just for the oscilloscope, right? And then this kind of mess over here just connects the wires coming in from the encoder basically to wherever it has to go, whether it's the oscilloscope or on the Arduino itself. So if we knock this down to bare minimum and we actually plug these right into the Arduino, I mean, a lot of this would disappear. So I think looking at a schematic is probably going to be 100 times better. Circuit's pretty simple. You can see we have the Arduino there on the bottom left. Right above the Arduino is the symbol for our power supply. To the right of that is the transistor. In this case it's an NPN, and we're using a tip 120. And then to the right of that is the motor and encoder. So in this slide we just have all the common grounds wired. Adding the motor driver wiring, you could see that we have a wire coming out of the top of the power supply going into the collector of the transistor, and then the emitter of the transistor is wired directly to what would be the positive of the motor, and then the motor goes to ground. So coming out of pin 10 on the Arduino, we have a current control resistor going to the base. And then in this configuration, if you apply 5 volts, it will basically act like a switch turning on the motor. And if the power supply is at 5 volts, it'll dissipate almost no power through the transistor. But because the Arduino only has PWM, what's going to happen is that transistor is going to turn on really fast. And for a motor, it's fine because it can't react that fast. But what we're going to do is put a little filter in there to stop that. So it sounds really complicated adding a filter, but really all it is adding a capacitor to ground, right? And I'm not going to go into how to design an RC filter, there's tons of stuff on it, but just realize all it is a one resistor and one capacitor. And you already have the resistor basically controlling the current going to the base, so all you're doing is adding a capacitor, which essentially just dampens that out. Finally, we wire up the encoder, and on a normal quadrature encoder there's 4 wires, right? Power, ground, and then 2 signal wires. So shown here we have the common ground, and then we're powering just right off the 5 volts from the Arduino. And then we take pin 8 and wire it to the single encoder channel that we're using. So remember, this is an A quad B encoder, but we're just servoing to a set RPM. You don't need both. Software is pretty simple, and I'm not going to go line by line, but a couple notes here. The comments that show up in green are just because I was using idle to display it because it breaks out the colors pretty nice. So just kind of ignore the hash in front of it. It's really just the 2 slashes for the Arduino code. That's why some of them are green, some of them are white. The software is broken into 4 parts. 3 parts are shown on the screen. On top are global variables and declarations. In the middle is the setup loop, and on the bottom is the Arduino specific serial event loop, and that's just straight out of the example there. The 4th section is the main loop, and that I have broken down into 3 sections. The top one is your serial event handler, so when you send a command, what you're trying to do is change either the set point or any of the gains. And to make it simple, I just send all 4 every time, so set point and 3 gains. And then all that does is when that serial flag is flipped, it just goes through, pulls each of the 4 parameters, converts them to numbers, and then saves them in their designated place. On the bottom is you're basically just printing out your calculated frequency, and in the middle it kind of gets more complicated, so let's look at that closer. If you look at the green comment tags on the right, the basic process is to collect a bunch of frequencies, right? And what you're trying to do there is filter across multiple. So you collect them, and then filter, and then use that to set or to run your PID algorithm and then output some control parameter. So the first part, collecting the frequencies, all I do essentially, like I said, I wait for it to go low, count, and it returns the time that it was low. Wait for it to go high, it returns the time that it was high, and then add them together and divide by the time, and that gives me the frequency. So with that individual calculated frequency, what I do is put it into an array of a constant width and then run that for loop, essentially, or run that in a for loop for the number of times that I specify in that array. In the second part, all you're doing is using a moving average. So essentially you take every parameter in that array and then average them all, return the averaged value, and then I call that my filtered, and then that's what actually I try and servo to. So if you try and calculate just once, if your algorithm messes up, you're going to get a lot of noise in your PID. So by filtering across multiple values, it's going to be a lot more stable. This generate control response is sort of the meat and potatoes of the PID algorithm. So let's look at that closer. All we've done here is split this section so it's a little bit more digestible. So on the top, you have essentially all of your pre-calculated error terms. So if you think about what is my error, well, I want to take my calculated frequency and subtract it from my set point, right? And that tells me how far away from where I want to be I am currently. Then the derivative of the error would be what's my error now compared to what it was the last iteration. Okay, so that's just my derivative of the error. And then, of course, since once you calculate that, then you save the current error as the previous error for the next time that it runs. And then your integrated error, you just sum this error to the running, so it's like a running total. And you would think that this would kind of go out to infinity, and sometimes it does, and the Arduino is sort of sad in that you really have to watch that. But if it's oscillating around the set point, like going too high and then going too low and going too high, they sort of just cancel each other out, right? Like the positives cancel out the minuses. So with the Arduino, you really have to watch that, but it's not too bad. The next line, this control line, is the basis for this entire discussion. It's one line of code that controls this entire thing. So if you look at it, there's three parts, right? Your proportional gain times the error, your integrative gain times the integrated error, and your derivative gain times the derivative of the error. And what each of these three parts does is think about if you're driving coming up to a stop sign. You're not just going to pick a level to slam on your brakes. What you're going to do is if you're going really fast, you sort of press really hard to get the car slowed down. But then as you're coming up to the stop sign, you kind of let off a little bit, right? So that would be the proportional term. So if you're really far away from your set point, what you want to do is apply a lot of corrective action up front, and then as you sort of come in towards your set point, you want to let off. Okay, that's just a proportional term. So your integrative term is like, so if I slam on my brakes and the car stops 20 feet from the stop sign, well, there's still kind of a little bit ways to go. So what the integrative term does, it says, well, I'm too short, but my proportional gain is too high. What this does is it's going to have an error that's opposite sign, and then it's going to compound. So the longer you sit there, the longer that term accumulates, and your control response goes down. Same thing if you're targeting for position, we'll say, and that's kind of the car example. If you overshoot it, what the integrative term is going to do is actually, again, increase the signal with an opposite sign, and it's gonna tell the car to come back. You need to come back into reverse, okay? And then the derivative error is like,
if you're not paying attention, for example, and you look up and there's brake lights, right? Your first instinct is to slam on your brakes. But if you're in an old car, that's horrible. So what the derivative term says is if my response is changing too fast, slow it down. So it just kind of damps the whole thing out. And that's really the three terms. And I recommend sort of building one of these to really understand what they do. But the three terms here are like 90% of control theory, okay? And then there's, of course, how to tune them and stuff like that. But just build it and play around with them. It's kind of the only way that you're going to learn. The third section is really optional, and really all we're doing here is we're saying, well, I'm using an 8-bit control. You know, my PWM signal is essentially 8-bit resolution, and it can't be negative and it can't be over 255, right? So I just, in the first 4 lines there, I just basically cap it. So if my signal for some reason does go negative, I think if the motor's not moving and the two pulseIn functions time out, they actually return -1. So it's possible to get a negative value. So let's say if the control algorithm returns a negative value, make it 0, and then if my integrative error is so high or something like that that it returns a value above 255, make it 255. And then in the final line there, really that's the deadband compensation. So say if the motor is sitting there doing nothing, I'm applying no power, it's not spinning, I have to let my integrative error ramp up to about 1.5 volts to even get that motor to think about spinning. So really all I do is remap 0 to 255 into 1.5 volts to 5 volts. But that's optional. And then of course in the last box, all you're doing here is, if you want, print the control response, and then that really gives you an idea without looking at the oscilloscope or anything about what the value is returning and then how fast it's changing, things like that. And then obviously you need to output your control response on the PWM pin.
Even though this setup works pretty good within the parameters that it works, okay, there are a couple limitations. So let's kind of step through them. So for one, the Arduino is 0 to 5 volts, and this is a 25 volt motor, right? So when they size the coils for the motors, they basically tend to size it so like full drive gives me sort of full power or whatever like that. But since we're using 1/5 of the power range, I think the deadband is from 0 to like 1.5 volts. So when it's at 1.5 volts, the motor doesn't even move. So we're really operating in sort of this really narrow range. So our control range is from, so like 0 RPM to like, I don't know, maybe 30 or 40, right? So we're really in that sort of cogging section of that motor. So what you can do is you can flip the transistor. Right now we have it in series. We just have a transistor in series with the motor, and we have it first, okay? So when you have it first, when the power comes from the supply, goes through that transistor and then through the motor to ground, it's a lot more linear. So it's easier to control, but you only have range. You have 0 voltage amplification. So even though this power supply can go up to whatever, 60 or 100 volts, we can only use 0 to 5. So if we put the transistor on the bottom of the motor in series after the motor, you can use the full voltage range because now you have voltage amplification, but the problem is now it's very nonlinear, and then it comes back to the loop speed on the Arduino. So in order to have really sensitive control over what you would need to if you put that in the bottom or in series after the motor, you have to have a really high loop speed to correct really fast. So what's happening right now is two things. You need really high loop speed, and you also need a very consistent loop speed, which the way this Arduino is programmed It doesn't happen. So right now we're waiting for the signal to go low, and then we time how long it's low, we wait for it to go high, and then we time how long it's going to go high. We add those together, and then that's how we calculate our frequency. That's really the wrong approach. You should have a set time and then count the rise, the number of times the signal rises. So because we don't have a consistent window when we're servoing, our effective gains all change as that window opens and closes. So when the motor stops, yeah, we can crank our gains up to get it back going, but what happens is when it's in that non-linear region, it just turns it up to like 25 volts, and then the motor goes crazy, and then it just cuts the power immediately, and the motor shuts down. So you really have to have those consistent parameters. So basically what happens is our integrative error takes a really long time to come up because our gain is set low, but then once the motor starts spinning, right, so think about this, the motor's not moving at all. It's waiting for the signal to go high, so we're not getting any clicks on our encoder, right? So basically waits until the cycle times out. So I don't know why on this software you can't like put the timeout time to something low, but for some reason, I don't know if it's a bug, but it's just basically not working. But even if it was, the window has to be large enough that at low speeds, so like maybe like right when that motor first starts to turn, it picks up that really wide band, right? So your timeout time has to be something like, but even if it was 500 clicks, right, where like the motor's barely moving and it's at a kilohertz, right? So even if we set it like minimum 500 hertz, it should still work, but I can't get it to work on the Arduino, right? So that kind of opens up the next challenge. So because this motor has like 1,000 clicks per revolution, our signals frequencies are really high. So again, the Arduino is probably not the best tool, but it'll do it. So when I put the motor directly up to the power supply, I can repeatedly get calculated RPM that matches what it is on the oscilloscope, or I'm sorry, not RPM, but frequency off the encoder that verified by the oscilloscope. It's repeatable up to about 5 kilohertz, which is pretty good for an Arduino. But but what does that mean in RPMs? It's something like 30 or 20 RPMs. Think about it. That's like 1 revolution every 2 seconds. So I mean, that motor's really moving slow. So coupled with the fact that it's a 25 volt motor and we're only using the first 5 volts, to apply to it, our loop speeds are variable. Our loop time is variable, and then our timeout doesn't work on the Arduino. We're sort of stuck within this control region of about like, the lowest stable frequency that I can get off the encoder is something like 1.7 kilohertz, and then at full 5 volts to the motor, it's only at like 3.2. So we're in this sort of narrow band. But anyway, I think that it's enough to demonstrate that the principle works, and then the software is super, super simple. Anybody can do this, just pick your hardware a little bit better, and how would you know unless you tried it, right? So there's, like, I'm not NASA, and that's the crazy part, is like when you launch a rocket, it's not like, all right, we're gonna do a test launch, get your hands on the PID dials. No. There's ways to calculate what your control parameters need to be so that when you launch a rocket, they're perfect. And it's crazy that they actually do it, but for me, I just sit there and twist them, right? And for most people, and for 90% of the controls world, that's how they do it. They tune their PID parameters and then set them, never touch them again until something changes on the machine. But anyway, this is it. Hope you enjoyed it, and we'll see you next time. Thank you.